Okay, so I'm going to do the example that we did in class on Thursday in this screencast, just because I talked with some of you after the class and realized there were some sort of fundamental concepts that were causing some problems. So I'm going to do this screencast so you can watch it over and over and make sure that you understand, because this problem that we're going to do here is a very basic problem that touches on the basic concepts, and that you need these concepts to apply to the more difficult problems that you might find on the homework. Okay, so in this problem you have a boy of mass 40 kilograms sliding down the spiral slide at a constant speed, such that his position measured from the top of the chute has components r equals 1.5 meters, theta equals 0.7 t radians, and z equals minus 0.5 t. You want to find now the components of the force Fr, F theta, and Fz. So those are cylindrical coordinates that the slide exerts on him at t equals 2 seconds. Okay, so right away you see look at what the problem is asking for. So it's asking you to figure out the components of the force, and it's asking you for the cylindrical coordinate system. So the first thing when you get these problems is to do the kinematics first. And when I say kinematics first, that means let's get the accelerations and the velocities. And so we're going to do this problem in cylindrical coordinates because the question is asking you to find the forces in cylindrical coordinates, and this is a perfect example where his motion is very easily described with cylindrical coordinates, because r is pretty much not changing with time, theta is moving, and he's going down in z. So you can it's really got a simple motion, like simple cylindrical style motion, so it can be described just by these r's, thetas, and z's. So we know r equals 1.5, theta equals 0.7 t, and z equals minus 0.5 t. So r dot is basically 0, theta dot is 0.7, so this would be in meters, it would be in radians per second, and z dot is minus 0.5 meters per second. Alright, so we've got now the velocities, and now we'll get the acceleration. So r double dot is also going to be 0, theta double dot is going to be 0, and z double dot is equal to 0. Alright, so there's no r, theta, or z components of acceleration, and these are the velocities. So now what we want to do is, now these are the r double dots, the theta dots, these are not the acceleration components in cylindrical coordinates. This is just the changes in r, theta, and z. And what you really need is, what you really want to find out are the velocities and accelerations. Alright, so then if you go back to your notes, you have a description in the cylindrical coordinates of how to define acceleration and velocity in terms of these r's and theta dots and z's. So if you remember there, Vr was just r dot, V theta was r theta dot, acceleration in r is r double dot minus r theta dot squared, and acceleration in theta is r theta double dot plus 2 r dot theta dot. And z acceleration, basically velocity in z is equal to z dot velocity, acceleration in z is equal to z double dot. Okay, so now we've got this down. So now we've got described the full kinematics, and I want to sort of make sure you understand this acceleration and radial component, because this is important for this problem. You can see that there's a component, this r double dot component, and that's just any motion that the boy might be doing in accelerating this way, sort of away from the boy's r coordinate is changing with time. However, you see that there's this other component right here, and that's that centripetal acceleration. And you can see that there, in that case, it depends on the velocity of this theta dot. So how much rotation the boy is doing over time. Okay, so keep that in mind. The boy can have an acceleration in the r direction, but not be increasing in r. That would be this first term, and that's simply because the direction is changing with time. So there's an acceleration that's constantly pulling the boy into the center of the slide, kind of like the same as gravity holds the planets rotating around the sun. So in this case now, the boy is being pulled to the center, and that's what this question is asking you for. It wants the components of the force that the slide is exerting on the boy to pull him into the center. That's what's going to come in this FR term, but we'll get to that in a second. Let's do the free body diagram. So this boy, let's just make him a circle just to make life easy to draw. He will have an FR component. There will be an F theta component, which is perpendicular but on the same plane as the F theta. These are the forces acting on the boy. And there will be an FZ component from the slide acting. So these are the forces that are acting on the boy, potentially, from the slide. So the boy is this mass M, and there are these forces acting on the boy. FR, FZ, and F theta. Now the boy has a mass, and so therefore he has a weight, and so the boy has a force due to his gravity that's downward. Okay, and that is in this direction, and that is the boy's weight, which is equal to mg. So these are all the forces in the problem. Now what we want to do is we want to use the sum of the radial forces is equal to the mass times the acceleration in the radial direction. This is Newton's laws of motion. And what this is telling you is I will sum all the forces in R, and any forces left over will result in an acceleration. Those are the unbalanced forces. So for example, if the boy was just standing still, or he's just standing on the outside of the slide, he would just have a weight downward. There would be a normal force pulling, coming from the ground upward. So let's say let's take the simplest case where the boy's just standing. He'll have a weight downward, and there will be a normal force upward, force of normal, that the Earth is applying on the boy. The sum of these forces would be 0 because the acceleration would be 0. The boy would have 0 acceleration, so that means that W would have to equal Fn. Now, let's see how that's going to apply to this case. All right, so we have Fr is the sum of Fr is equal to mass times the acceleration. So now let's sum the R forces. So let's first, since we found AR, we're going to solve for MAR. So let's do that. So the mass of the boy is 40 kilograms times the acceleration, which is going to be R double dot minus R theta dot squared. And that has to equal the sum of all the forces in the R direction, which is, since in this case it's the force that the slide is exerting in the R direction. Now, some of you might be confused now and saying, well, why is the boy not applying a force on the slide? Clearly when I go on a slide, I'm pushing against the edge of the slide, and this is a fundamental concept that I'm hoping to clear up for you here. So the reason that the boy does not have, you can think about it mathematically, the reason is the mass, you can see that his weight is in a downward direction, and the R component, so if you looked at his weight is downward, and R is perpendicular to this. So this force that he has, his mass downward, has no component in the R direction. And now that force that you think that the boy is using to push on the slide is not a real force. That is a centrifugal force. Okay, so for purposes of Newton's laws, this is not a real force. And so that force, what that is basically the boy wants to go in constant motion. So it's just, you can think boy just wants to move along in a straight line. And the slide is applying a force that's pulling the boy inward into the center of the slide constantly, just like the pull of the sun. So the dominating force that's causing the rotation of the planets around the sun, so if you have a sun and planets going around, it's the force that the sun is pulling on these planets is much, much larger than the force that the planet is pulling on this massive sun. So for the purposes of describing the motion, it's the centripetal inward force. Those are the real forces, because in Newton's laws, description, force is equal to dp dt, or ma. So the boy is it's basically changing, the slide is changing the boy's acceleration constantly. And I know it's sort of a difficult concept, but this is the centripetal force, and this is a real force, and we're going to be using this concept a lot in this class. So the boy is not applying a real force on the wall. It's the slide applying a force on the boy. And if this concept still is confusing you, please come and talk to me, because it's really an important concept to try and grasp for this system. Okay. I mean, another way to take it is, you have to look at these forces in an inertial reference frame. So if you're just looking at these, at the motion of the boy, all you would see is the boy wanting to go in a straight line, and the slide pushing constantly this way. That is a centripetal force. Okay, so you've got this. You've got the force of the slide. Now we're going to take this, and r double dot is 0. And so there's only the mass times the acceleration. There's only this term here, which is the centripetal acceleration. And that's r theta dot squared, which turns out to be minus 0.735 meters per second squared. You multiply that by 40, and then so the sum of the forces in the r direction, which is just going to be the force that the slide exerts on the boy, is minus 29.4 newtons. And so this force is in the minus direction, so it's basically towards the center in this direction. So it's opposite towards the center of motion, opposite this r that we defined as positive. This is positive, then the force is negative, it's in this direction. Alright, so that's Fr. And now the other ones are F theta is easy because there's, again, because this theta component, so we can, I will erase this. So F theta is again perpendicular to W. I kind of putting down in 2D. And so there's no component of the weight in the F theta direction. So the sum of the forces in F theta is equal to 0, and M A theta, is, this is 0, this is 0, so you just get equal to 0, and this is the force in the theta direction is just 0 that the slide exerts on the boy. Alright, and finally the last one is the force in the z direction. So the sum of the forces in the z direction is going to be equal to mass times the acceleration in the z. So in this case, the acceleration in the z direction we found to be 0 here. So that means the sum of the forces in the z direction have to be equal to 0. So now we'll look at the free body diagram, and it shows that the boy's mass is downwards, so that's the W, his weight. And actually I'm going to call this direction positive. So there's a normal force that the slide is exerting on the boy, which is in the positive upward direction. So that would be force, we'll call it force Z of slide, let's say, minus the weight of the boy, and that has to equal the mass times the acceleration of the boy, which we already said was 0. So what this tells you is that the force in the z direction is basically just equal to W. So force Z of the slide is equal to W, which is 40 kilograms times 9.8 meters per second squared. And so that's equal to 392 newtons. Alright, so that sort of solves that problem, and if there are any questions anymore, just let me know. Hope this clears up centripetal forces and Newton's laws. Alright, thanks.